Hi everyone, and welcome to the Fundamentals of AI. We have a jam-packed program tonight, so we might just get started and other people can join in as they come. I'm so excited you guys tuned in tonight. My name is Emma Cooney, and as the ambassador for the Young Women Leaders in AI, I'll be your host for this evening. I'm currently in Year 12 at Cannon Hill Anglican College, and like many of the other senior students online tonight, I'm really excited to be learning about the more technical side of AI. Tonight is, our guest speaker is Dr. Ruth Pearson, who will be joining us all the way from England and giving us a technical lecture about machine learning for the first hour of this evening's session. This will then be followed by an interactive problem-solving task for the last 20 minutes. Dr. Pearson has her PhD in cosmology and is now working in the forefront of the AI industry as a machine learning engineer and data scientist. She has a wealth of experience in all facets of the STEM industry. And so without further ado, I'll hand over to Ruth and she can get this webinar started.
Thank you, Emma. Thanks for that lovely introduction. I will let you stop sharing your screen and I'll just share mine instead. So, okay, hello. Hopefully you can see my slide now. Emma, if you can't, please shout at me and tell me that you can't see it. Thanks again, Emma, for the introduction. Thank you for inviting me today and for organising this session. So I'm going to talk about some of the fundamentals of AI, particularly some of the maths. We do have time at the end for questions, but if you have any questions along the way, please either interrupt me or write in the Q&A. So what will happen is Emma will be keeping an eye on the Q&A for us, so that if you do have a question, she can interrupt me and we can answer it if you want to ask along the way. If you have a question, please ask it. Don't feel silly. No question is too small. If you are wondering about it, someone else will be wondering about it too. Okay, so before I get started, I just wanted to introduce you to me. My name's Ruth, and this is a picture of me and my cat Flippy, who is the light and joy of my life. I am originally from the UK. I completed a physics degree at the University of London at a place called King's College. And then after that, I went on to do a PhD in cosmology. Cosmology is a branch of physics, which is the study of the universe as a whole. So we care about the really tiny things as well as the really big things. And so I did that at the University of Sussex, which is also in the UK. But I ended up spending most of it in California at the University of Stansted. Stansted, that's an airport. At the University of Stanford University, which is in California. The reason I got in touch with Emma and the Queensland AI Hub is because from 2014 to 2020, I've been living in Melbourne, where I've done a few different things, but mostly been working in public health statistics and AI consulting. But I moved back to the UK in June this year, and I'm currently a senior research scientist at Mars Pet Care. So now I have my dream job, which is developing AI tools for vet medicine. So I get to predict disease, for example, in cats and dogs. So I want to tell you a little bit more about me as a person as well. So if you haven't already noticed, I love cats. I'm also queer. So what I mean by that is I identify as queer, lesbian, gay, or just generally as a member of the LGBT community. I have a twin sister whose name is Lucy, and you might meet her later on in this talk. I'm an intersectional feminist, and I enjoy circus arts, particularly acrobalance, and I love listening to true crime and comedy podcasts. Okay, so I think my screen just went off. If that happens, I will fix it, but Emma, you will shout at me if it's broken, please. Thank you. So, AI, I'm sure a lot of you are interested in AI. You probably know a little bit about it already, and that's why you're here. So there are many applications of AI already in our daily lives. And you probably know about some of them. There's a list to the left of this slide here, examples like Siri, the spam filter on your emails, Facebook, WhatsApp, Instagram, Snapchat, anything that recommends friends to you, automatic photo tagging, or shows you might like on Netflix. So as well as being a huge part of our daily lives already, there's also many, many opportunities for AI to improve our lives in the future. And so one very frivolous example of AI that is my favorite is this one here. So I just thought I'd share it with you, is that now we even have AI which can take a picture. So as input, piece of AI takes this picture, which is unfunny. So this is a picture of two people sitting at a table, not very funny. And then the AI trains itself to be able to output from that image, this image here, which is two dogs sitting at a table, which I think you'll agree is very funny. Another example, this innocuous picture of a park, we input that into our funny AI, and it outputs a raccoon on a scooter. So there's really many things that we can use AI for. Okay, so first of all, let's just introduce a little bit how machines learn. So the human control center in the human body is made up of our brain, our spinal cord, and our nervous system, or our central nervous system. And signals are sent to and from and around our control system to different areas of our bodies, for example, to tell our muscles to contract, to pick something up, for example. And that happens by neurons traveling and around the body and receiving and sending signals. So neurons are very intelligent cells. They receive some electrical input, and then they process that input or transform it into something different, which they output to other cells or neurons. So these electrical signals are being passed from neuron to neuron, and each neuron changes them slightly. So then information in the brain is passed around in different ways by these individual neurons. So the human brain contains around 100 billion neurons, and they are a big neural network. So it is a big neural network, as it is a network of neurons. These neuron cells are a network in the brain. And so in AI, we use this concept of the human brain and how it processes information to design what we call neural networks. In code or in algorithms. And so our neural networks in code are networks, algorithms that we make that take information as an input, just like the neuron cells. And then the algorithm that we write contains a network of what we call nodes, or these neurons, which change or transform the signal that they receive and then pass it along to the next neuron. And eventually we can use this network to produce an output, which we can use to make decisions with. So neural networks come in all different shapes and sizes. Here are a couple of examples of pictures you might have seen. So they usually look like a lot of boxes or circles joined with some lines, but they look quite complicated. So how can we learn to build the basics of these and interpret or read or even design these neural networks? That's what we're going to talk about today, but there are three main ways that machines can learn, which I'll introduce first. So the first way is supervised learning. So in supervised learning, we have known categories. So let's say we have these pictures of Tom and Jerry. So this is labeled data. We know what the answer is. We know that these pictures are pictures of Tom and that these three pictures are pictures of Jerry. And our algorithm here, whether it be a neural network or something else, takes as input this labeled data, and our network is trained to detect Tom or Jerry for any given input. So at the end, the output we get is, oh, this picture is Jerry and this picture is Tom. So that's supervised. The other type of learning we have is unsupervised learning, and this is when the categories are not given. So we don't know who Tom and Jerry are. So you can see here we've got pictures of Tom and pictures of Jerry, but this is not labeled. We don't know what the answer is. And so in this case, our network tries to separate the input into similar categories, and what we get out is this unlabeled output. So here we have pictures of Tom and pictures of Jerry, but it's not labeled. It doesn't know that this is Tom. It just knows that, you know, these pictures look similar and these pictures look similar. So we've grouped them. The final one is reinforcement learning. And so reinforcement learning learns how to take actions in an environment in order to reach some goal. So for example, we can think about a rat in a maze. If a rat is trying to find a piece of cheese or some reward in a maze, it could, for example, get to a decision point and choose to turn left or right. And so reinforcement learning works by making one of those decisions and then seeing the rewards that it leads to, and then next time updating a choice so it leads you to do better. This is often used in video games. So this talk, I'm going to build on a couple of these ideas, but more specifically, I want to talk about an example of supervised learning. So this is an example where we will use labeled data to train an algorithm to make a decision. So that's that first supervised type of learning. I'll introduce a simple neural network. It's called the fully connected feed-forward neural network. And I'll show you how some of the maths you already know is applied in neural networks. And so some concepts I'll introduce you to are neural notation and model architecture, the loss function, gradient descent, and backpropagation. Okay, so I have a few slides which are colored in yellow throughout the talk. And these ones are to remind us of some maths that we already know. So the first one of these is functions. So I think you probably all know of the concept, the mathematical concept of a function, which we write by this equation here, y equals f of x. So the value y is a function of this variable x. So for example, y equals sine of x. So if we know our x value, we can calculate y by inputting our x into whatever function we have. So with that in mind, we're going to move on to something called neural notation. And we're going to talk about this using an example of the cool shop. So Lucy has a t-shirt shop, and she posts about her t-shirts on social media, and she has data about how well her t-shirts have sold in the past. And she would like to use AI to estimate her future sales. So, cool shop data. So this is the data she has. She's got different t-shirts, so t-shirt A, t-shirt B, t-shirt C, and she's posted them on social media, and she knows, for example, t-shirt A has got 3 likes and it has sold $70 worth of t-shirts. And she has a theory that she'd like to test, which is the amount of sales she makes somehow related to the number of likes that a t-shirt gets on social media? So we would like to learn how to represent this problem in such a way that we can use a neural network to help us. So first, let's see if we can represent this theory in maths. So in a mathematical way, we can write out this equation here, which is that sales equals W times likes. So this W here is a parameter. So we don't know what this is. It's some unknown value, but it's a guess. It's like maybe sales is related to the number of likes. So we put this parameter in that we're not sure about yet. Okay, so you're probably familiar with this mathematical representation, but what we want to do now is use what I'm calling neural notation to draw what's called a graph, which means the same thing but in a diagram form. And that's what we've got here. It looks like a small little piece of a neural network. So this diagram has some circles. These are called nodes or neurons. And it has this line, which is a connector. Or we also call connectors weights. So we want to know sales, and we know likes, and we're guessing some parameter W. So this diagram means that this sales node equals this line that connects it, multiplied by the number of likes. So you multiply the line with the node that it came from, and that is the answer for what this node equals. Okay, so what if the amount of sales also depends on the number of shares in social media? So now we have two of these orange input nodes, or likes and shares. So likes and shares are something that we call features. So they're things we know about. But now we've had to add this other parameter W2. So we've renamed our W because we've got more than one parameter. So now we've got W1 and W2. And so if we wrote this in our mathematical equation form, we would have, okay, so now sales is equal to some number times the likes plus some other number W2 times the shares. And the way that we draw that is like this. So our sales here is still what we want to find out, and it is equal to, the value of this node or this neuron is equal to each line times the node it came from plus to all of the other ones. So we say the sum of. So W1 times likes plus W2 times shares. And so this looks like a little piece of a neural network. And this is almost, it almost is, but there's a couple more ingredients we need to add. Okay, so the structure of neural networks we've seen looks quite complicated. There's lots of lines and connectors and circles. And the reason for that is that when we have a lot of neurons or nodes, this allows us to represent more complex processing of the input or the data. So what we're going to do here is add a hidden layer for more complexity. So we've added something in between our input layer, which has shares and likes, and our output layer, which is what we want to know. We've added this node here, and it's on its own in its layer. So how does that change things? We've added it for complexity, but how does the maths work out? So we've rewritten our equation. So now the value of this node here, this middle node, is equal to W1 times likes plus W2 times shares. And we need to propagate that through to know what our sales is equal to. So our sales is equal to W3 times everything that was in this node, which we can write by putting brackets around our initial part of our equation and multiplying by W3. Okay, so what happens if we do that? Okay, so what happens if we do that is, this is the same equation, this is our diagram. If we assume some values for our parameters or our weights, let's say we choose W1 equals 4, W2 equals 3, and W3 equals 2. Well, then we can add these numbers in. First of all, we take our W3, which is 2, and we would multiply out, well, W3, so 2 times 4 equals 8, so 8 likes plus 2 times 3 equals 6. So then we would get as an answer sales equals 8 likes and 6 shares. So in this situation, we could have just chosen W1 equals 8 and W2 equals 6. So this W3 actually hasn't added any extra information for us here. So we say that it's redundant. And so that's because there's no added complexity by adding this parameter, because we could just make a different choice of W1 and W2 because we're free to do that. And so we can still only represent what's called a linear problem. So we need one more ingredient to make our little piece of neural network. Okay, and that's an activation function. So we add activation functions to add non-linearity to our problems. I'm just going to drink some water. So here we've got our same picture, but we've added, in our node, I've added this thing f of a. So this is just to represent a function. A just means it's an activation function. We haven't specified what it is yet. And it is a function of this wi. So wi is a vector of the weights that are included in the ith layer. So for example, this neuron knows about weight w1 and w2, and that's all it knows about. So W1 is just a vector of W1 and W2. So I could have written here that this is a function of W1 and W2, and the notation is equivalent. This node here, W2, this Wi, which is W2, it depends on both W1, W2, and W3 because we've got this extra input coming into it. So as we go forward through our network, our nodes contain more of the weights from previous layers. So let's say we do this. What does our equation look like? So this is what our picture looks like, and our equation looks like this. We have now that our sales is equal to this first blue bit, same as before, our sum of our weights and our inputs, but wrapped in this function. So this becomes the input into whatever activation function we choose. And then that value multiplied by W3, or weight 3, becomes the input into our purple activation function. And then we evaluate the function, and then we get sales. And so the job of training a neural network is to use data to learn what these weights are. So we've added this activation function on these two nodes, but we don't need it on these ones because these are our inputs, these are our features, these are things we know from data. Okay, so we have a choice about our activation function. Basically, we can choose whatever we want, but there are some kind of common choices. So this is called the sigmoid function. It's a smooth and well-constrained activation function. So, for example, if our input here was 5, for example, we would evaluate this. When x equals 5, this function equals 1. When x equals -5, this function equals 0. We say that it's well constrained because it can only go between 0 and 1, so we'll never get huge numbers. Even if we get a big number coming in, we'll always get a value between 0 and 1 coming out. And that can be useful for us because big numbers cause us problems, and also 0 and 1 numbers between 0 and 1 is how we choose to represent probabilities often. Okay, so another common activation function is hyperbolic tangent, or tanh, or tanh, whatever you'd like to call it. And this is more severe, but also well constrained, because here, this function will only give you a value, regardless of your input x, the y value will always be between -1 and 1. It's more severe because if we look at this, let's say we calculated this function at -5, we'd get a value of 0. But if we calculated this function at -10, we wouldn't get a value of 0, we'd get a value of -1. But if we calculated this function with x equals -10, we'd also get -1. So it doesn't really differentiate much in these areas, only in this bit. Another activation function, which is the one we'll use, is called ReLU. And this is more forgiving, but it's not well constrained. So you can see here that anywhere where x is negative, this function will return 0. So it doesn't let us have any negative values. It's always 0. And then from 0, it's just a linear function. So if x equals 5, then y equals 5. If x equals 10, then y equals 10. One issue with this is that if x gets really, really big, then y gets really big, really big. So all to say, we have a choice about what we choose for our activation functions. For this example, we're just going to choose ReLU activation functions and see what that does for us. So if we write this down, we have our equation here where we had our activation functions. So now all we do is we take our ReLU function, and instead of writing FA, we've just written ReLU. So now we know we are going to calculate the value of this function for this input, and then multiply the answer by W3 and calculate this. So let's do that. To do that, we need to make a couple of assumptions, because we need to assume our features. So we need to assume what our inputs are, because we want a number, we want to know what sales equals, so we need to put some numbers in. So let's assume that our features are likes equals 10 and shares equals 3. And we also have to assume our parameter values. So we have to choose values for our weights. So let's choose 4, 3, and 2. And so you can see I've just replaced them here. And let's see how that follows. Okay, so here's our diagram. And now we can actually just calculate the value of sales using this function. So I've put in here, so we've got 4 times 10 plus 3 times 3, which equals 49. And we know that if we evaluate our ReLU function for some value of x that is positive, then y will be the same numbers. So ReLU of 49 is equal to 49. And so that gives us our purple ReLU, 49 times 2 down here, which equals 98. So we've calculated that our sales equals $98. Okay, great. So we can use this knowledge to understand what a simple neural network could look like for the cool shop, because that in itself is a small piece of neural network. So let's design something simple. So here I've added an extra feature. So our input layer has 3 nodes, so we can add 3 features. So we've got likes and shares again. We've also got number of comments. We've got 2 hidden layers, each have 4 neurons, and then we've got our output layer, which is what we want to know. So why does it look like this? Well, this is what's called the architecture of our neural network, and we are free to choose the architecture of our neural network. In practice, we choose, we make smart choices, and we might understand some things about our problem that lead us to choose specific architectures. One thing I want to tell you is that here we have many, many more of our W's. So we've got this one, this one, this one, this one. So we've actually got 32 weights. So we've got 32 unknown values that we want to learn. And so what we are going to use features as input to calculate the output for weights. And we don't know what the weights are yet, and we're going to talk about how we find those. So in order to do that, we are going to talk about linear regression as a motivator for a neural network, because this will help us understand how to build and train a neural network. Okay, another math slide. So straight lines. So you're probably all familiar with this equation of a straight line. You might know it as y equals mx plus c. I've just written it, instead of m and c, I've called our parameters w1 and w2. And if we make different choices for w1 and w2, we can draw our different lines here. So this one has 1 and 0, this is 1 and 10, this is 5 and 0. We get a different line. The y-intercept is different and the slope is different. So we'll use that to help us. Okay, so let's try and do some linear regression at the cool shop. So we've got this table. Here we've just gone back to one feature, likes, and sales is what we want to know. So we'll write this down in our straight line notation. So we'll say, okay, sales is equal to W1 times likes plus W2. And we'd like to see if there's a relationship between the number of sales and the number of likes. A linear relationship would mean that a straight line more or less maps out our data points. So we've plotted our 6 data points. So this is what we know. And it doesn't look like it's exactly a straight line, but it looks like more or less we could probably plot a straight line. So draw a straight line through here. So let's try. Okay, so first of all, let's try W1 equals 1 and W2 equals 2. So I've plotted our black line here. This is our try 1, and we can see our data points. So these points here are quite far away from the line, even though the first 2 look quite close. So with these red arrows, I've drawn the distance from the line to the data points, so we can get a sense of how far away our guess was. And the error, the total error, so how well we did in choosing this line, I've represented by turning each of these red lines by 90 degrees and putting them next to each other. So this is our error. So this isn't a great guess. So let's try another one. So let's try W1 equals 4 and W2 equals 0. Okay, so now this looks like it fits a little bit better. Our error here has got less. So if I just flick back, that was our error before, and now when I add all of these errors together, it's a bit less. Great, let's have a third try. So now I've chosen W1 equals 2 and W2 equals 1. So now the line that produces fits quite well. So the only data points it doesn't touch are these two, and you can see that this is quite a small error. Okay, so our line fits our data better when this error, which we've represented here with these red arrows, is small. So in practice, we rarely explore different parameter values. We rarely guess different values. We have a way of doing that, which we'll see in a minute. But our objective here is to get our model here is our straight line, to match the data points as closely as possible. And so we find the best parameters by minimizing the mean squared error. So this equation, so MSE stands for mean squared error. So this is error, let's say this is error, and this is equal to 1 over n, where n is the total number of data points we have. So if you remember, we had 6, and then it's the sum of this quantity squared. So this quantity here is the difference between the known answer, so this is our known number of sales, and the model prediction. So this yi with a hat is the model prediction, so what the straight line says the value is. So we can call our straight line the model, and when we found the best parameters, we say that we've trained it, but we use this error function to try and find those best parameters by minimizing it. So let's remind ourselves of our model and what it is. So it's just this straight line. So all I've done here is just, instead of putting that yi hat, I put the value of that, which is just our parameter values and our likes. So this is our known number of sales. And so we want to minimize this quantity. And once we have done that, we know that we have the best value of our parameters and that our model is fit. So the training part is how we change or evolve these W values to minimize the error to get our line as close as possible to our data points. And so this is an important concept. And so we can do something similar in training the cool shot neural network. So these principles of fitting a straight line to some data points will help us understand how to build and train our neural network. So here we are training the cool shot neural network. And so there's a lot going on, so let's go a bit slowly. Remember, we have our chosen model architecture here, and we have our input layer. Our input layer was our likes, our shares, and our number of comments. So we put those, for each t-shirt, we feed those values into our input layer. Our output layer is the value of sales. So, okay, for that t-shirt that got those comments, shares, and likes, what were the sales? This here you will recognize from the previous slide, but I have something important to tell you about it, which is that in machine learning or AI, neural networks, any of these words we want to use, we have a special name that we use for the error. So we still want to minimize error. But now, instead of calling this the mean squared error, I've called it the loss function. So it's exactly the same thing, but I've given this new name, loss function. So mean squared error has been around for a long time. As we have started using machine learning and AI, we generalize our error into something called the loss function. And often, particularly in simple examples, our loss function is just the mean squared error, but there are lots of other ways that we can measure error. But in our case, we've chosen this value here, which is our mean squared error, which we explored before, as our loss function. And so here are our steps. So training our neural network means we want to know what are the best values of our weights, W1, W2, all the way to W32. So let's choose some values. So at the beginning, we don't know what the best values are, so we'll just choose some. We'll set them all to be whatever the values they are. And then in our step 2, we input each t-shirt's information, each t-shirt's features into our neural network and get our sales. So input t-shirt 1, okay, we've got sales 1, input t-shirt 2, now we've got sales 2, input t-shirt 3, now we've got sales 3. And so we do that with all of our t-shirts, and then we're ready to do this third step, which is calculate the loss, because this sum goes, this notation here, it means sum, and we're summing across our t-shirts. So we're adding up this error or this difference for each t-shirt, and the total error is our total loss for some given choice of these parameter values. Okay, so we calculate the loss for our choice of our parameters, and then we repeat. So we keep on choosing different values of W1, W2 to W32, feeding our data through, calculating our output, which is our sales, and then calculating the loss, and then we would keep doing that until our loss is minimized. So to help us do that in a more efficient way, I want to talk about gradients. So this is another math slide. So you're all familiar with this concept of a function. So we've got this function here, y equals x squared, which looks like this. And we can take the gradient of that function, or we can differentiate that function. So dy dx for y equals x squared is equal to 2x. So I've plotted that too. And we know that if a function has a minimum or a maximum, then at that point here, the gradient will be equal to 0. And so here, y equals x squared, we can see a minimum, and our gradient, which we've plotted here, is indeed equal to 0 at that point. So we're going to use this to help us. So in practice, we are not going to just choose lots of different values of our weights. We can't just choose 32. Well, we could just choose 32 every time, try something different, try something different, try something different, but that's not a very efficient way of doing it. So we're going to use this, we're going to use gradients to help us. And so we minimize the loss with a gradient descent algorithm. So I'll just explain a little bit what the gradient descent algorithm is. So this is our loss function, which I've drawn in 3D. I haven't drawn it in 33 dimensions, so I haven't added all 32 weights. I've just added 2 weights and our loss. So how do we find the minimum value of our loss? Well, we can see that it's at this point here. We can see that our function has a minimum value down here, and we don't want to choose new parameters at random. So what we do is we choose a value, choose some value of our weight. So let's say we choose some random value of weights, and we start, what we do is we make an algorithm to say, okay, I've chosen these weights. Now I'm going to look around me in every direction and calculate the gradient close to me. And then my next choice of weights, I will make that choice based on where the gradient is going downwards, because what I want to do is go all the way to the minimum. So if I'm here, I can see, okay, well, this is the downwards direction. So I'll move here, and then I'll calculate my loss again by feeding all of my t-shirts through. And then I'll look around and say, okay, well, can I go down? Does my gradient point down any more than where I already am? And if it does, I keep on going. So keep on going until we get to this bottom place here. And so the values of W1 and W2 that we would like to choose for our trained or fit neural network are the values of W1 and W2 that represent the minimum of the loss function. Okay, so our loss function is a function of these weights. So in order to actually compute these gradients so that we can step around and explore the best parameters to choose, we have to compute gradients for our entire network. And so that's, you might hear that referred to as what's called back propagation. And so it's one long differentiation, because as you go further in your network, you have more and more weights included. Once we've calculated our gradient, we use it to help us find the minimum and take us down this slope. So you can think, if you think of a ball and gravity, if we let a ball go in this space, it would just roll down to the bottom. And so we want to write an algorithm that simulates that. And that's where gradients is important. Okay, so what happens next? Well, our network is trained when we have chosen the best values of our weights. So we go through that process. I mean, in practice, we have an algorithm do it for us. It's called gradient descent. And our network is trained when we've chosen the best value of our weights, all of our weights from W1, W2, all the way to W32. So at this point, in practice, we would like to know, well, how well have we done? It's trained, but does it work? So at this point, we do a test. So in practice, we would have saved some data to make sure that our trained model is working correctly and that it can generalize to new data. So that means that the network will make predictions that are correct, even when the input data is data it's never seen before. So we have our values, we have our trained network. And so then we are ready to use the cool shot neural network, because we've got our values of W2, we've trained it. So now we're ready to say, okay, I've got this new t-shirt. And as it would happen, Lucy has a new t-shirt. She has learned a little bit about neural networks and designed a t-shirt that says, I love maths. And so she's posted her t-shirt on social media, this new t-shirt, and the post has received 22 likes, 5 shares, and 3 people have commented. And now Lucy wants to use the cool shot neural network to estimate the number of sales that she will get for this new t-shirt. So here's what we do. She will input the data into the trained neural network to predict its sales. So we've got our input features like shares, number of comments. So she had 22, 5, and 3. And we know all of the values of these lines, and we've chosen our activation functions in here. And so we propagate these values through to the end, and we calculate the value of our output in the way that we did with our neural notation, but just on a bigger scale. And so our output layer here is $500. So we've input information, we've input for this t-shirt, and we've received a prediction of how many sales this new t-shirt will get. So to summarize, we have seen how the fully connected feed-forward neural network works. The reason actually that it's called fully connected is because each of these nodes connects to every other node in the next layer, and it's feed-forward in the name because each time each layer passes information to the next layer. And so what have we learned? Well, we've learned to prepare our data. So we've collected data for training. So Lucy had some data that she knew the answer for, so because it's a supervised learning problem. So we're training our algorithm or our neural network to make decisions based on what has been seen in the past, or data we already have. So we had our feature variables, our likes, our shares, our comments, and we had our target variable. Our target variable here was sales. It was what we wanted to know. We've chosen choose a model architecture. So how many nodes and layers will it have? We have a choice about that. And we have a choice about which activation functions we use. We've trained the model. So we've seen how to feed each training sample through our network and then calculate the loss for a given set of parameter choices. And we know that we need to minimize the loss using a gradient descent algorithm or something similar. And the model is fit when the best set of weights has been determined. And then we can test our model. So we say, okay, we've got the best set of weights. Does that generalize to new data? Are we confident that our model works? And then we're ready to use it. So for Lucy's new t-shirt, we took the social media data and we fed it through the model to predict the number of sales it got. And so Lucy got $500 worth of sales on her new t-shirt. And so the last thing I have to tell you is that Lucy invested the profits of her new t-shirt into making face masks. and face masks are now available from the Cool Shop. So that's the end of what I wanted to tell you today. I'm really happy to take any questions about the talk, the Cool Shop, or just about me or my experience in general. So I think Emma will help us with going through the question chat and reading some of them out, and then I'll answer them. Maybe we wait a couple of minutes for some to come in.
Yeah, that sounds great, Ruth. Thank you so much for your talk. Why don't I start off the questions? Give you, while we wait for other people to jump in. My question was to do with the activation functions you were talking about at the beginning, the ReLU and the etc. Those ones. How do you choose which one of them to use according to your data, and sort of what goes into those like decisions and which one you use?
Yeah, that's a really good question, and it's a very complicated question actually, and it's an area of research. So, for example, often what I'm doing is representing a probability. So I want to use, let's say I want to use information. Let's say we've got a human, and we want to use information about their health. So maybe we take a blood test and we have a few things that we measure in their blood, like number of red blood cells, number of white blood cells, how much glucose they have in their blood. And so those will be numbers. They might be, I don't know what a reasonable number is, but let's say they're like 13, 32.1, they'll be numbers. So in our network, if I got a network here, if I'm feeding like numbers through here, but the thing that I want to learn is a probability. So maybe my output is the probability that that person will get diabetes. So then I want my number to be between 0 and 1. So sigmoid is useful for probabilities. It's also useful if you're worried that you might get really huge numbers, because something to do with the way that we calculate gradients means that if we have a really huge number, if we get really big numbers getting bigger and bigger as they propagate through our network, then we get problems. Yeah, so I guess ReLU as a function, it stops us having negative values, but otherwise behaves linearly. But one of the problems is that it doesn't help us if we want to get, if we have really big numbers. So it really depends on the problem that you're trying to solve. And so sales, for example, if we wouldn't use sigmoid or hyperbolic tangent for the final layer of our Cool Shop neural network, because we don't think our sales is going to be represented as a number between -1 and 1. We might choose ReLU because we know there's no such thing as negative sales, and we want it to be able to be any value we want. So in practice, what people do is look around and see what other people have tried, maybe read some papers, and look at similar architecture choices for whatever problem that they're solving.
Yeah, thank you. That's really interesting. Thank you. So we have a question from Simon, and they ask, what's the best coding language for AI to learn? For example, like Python, or what would you suggest, Ruth?
Yeah, so I'm biased, and I think the answer is Python. But objectively, I think the answer might also be Python. So I learned to code using not Python, using other things. I would say that since I've been working in machine learning and AI, Python is what I have found to be the most prevalent language in my experience. That could be confounded by the fact that it's the language I use. But certainly if you use Python, it's very common, it's very popular, and the really useful thing about it is that there are loads of libraries, there's lots of tools you can use, and there's lots of online resources. So that, it's a very well maintained language, there's a whole community around it, so I would really recommend using Python. It's quite it's what's called like a high level language, so it's quite like it lets you do things without having to do a lot of like computational work underneath. So it's quite easy. I mean, I don't want to say that it's easy, but it's quite nice to interact with. It's very user friendly. There's loads of machine learning libraries. There's loads of blog posts and online resources. So I think, yeah, try Python.
Excellent, thank you. And we also have the question, with the neural networks, you had, I think, 2 hidden layers, and Sullivan's asking if you add a 3rd hidden layer, or I guess any amount of hidden layers, does it get more accurate, or what's the effect of doing that, or
yeah,
why
that's
would
a
you?
question. So generally speaking, the more layers or the more nodes we have allow us to transform our data. So if we think about our neuron cells in the brain, we said that we receive an electrical signal, we change it, we pass it on, and then the next one receives it, changes it, passes it on. So the more of these connections we have, and the more of these neurons we have, the more times, the more we transform our information, and that allows us to be able to represent more complexity. And so as we add more layers and more nodes, we can learn more complicated patterns. So in this example, I've used numbers as an input, but I'll just talk briefly about pictures. So let's say instead of learning about sales of a t-shirt, we were learning about we had an image problem, and instead of inputting likes, shares and numbers of comment, we were inputting pictures of cats and dogs, and our output told us whether we had a probability of having a cat or a dog. So if we think of it with images, the more complex our network is, the more complex the features of an image we can represent. So like a line in an image is represented in pixels by a whole load of zeros and then a whole load of ones, or a better way of saying that is an edge. So that's quite a simple feature of a picture. And so as we go further through the layers, we start to be able to represent, okay, well, maybe now we can represent circles, maybe now we can represent spirals. So it's kind of like the more complex features can be represented as we add more complexity to our model. That might sound a bit abstract, but I think thinking of it in terms of images is a bit easier to understand. But there comes a point where actually you add more and more and you might perform better, but there'll come a point where you don't want to add any more. There'll come a point where it won't pay off anymore. You won't get any better output. And that's why we just have to, for each problem, look around, see what people have done.
Thank you, Ruth. Yeah, that definitely makes sense. We have another question that I guess is more about AI and machine learning in general. And they ask, how do you see learning data science as an undergraduate bachelor's degree? Because many people say data science can only get serious when you do master's or a doctorate. And you should pursue maths or a computer science degree instead of doing an undergraduate. What's your opinion on that?
Yeah, well, because I come from a physics background, I learned how to code during my undergrad, but I wasn't very good at it and I didn't like it. I didn't really like writing code until I started, or maybe during my master's and PhD, I began to understand the benefit of writing code. But for a long time, I wrote very messy code. And so people from an academic background are well known for, particularly physicists, for not writing very clean and tidy code. So you have like the science background, but one thing that you often don't get in that background is the kind of like pure practical skills of how to write good code. So it took me some time, after finishing my PhD, to learn how to write code that wasn't a mess. So one of the benefits of starting straight away with a degree in, let's say, data science or machine learning, is that you would probably learn what's called best practices, or like good coding principles early. So I think it's definitely true that if you study science or if you study maths, you're very, very well suited for a career in data science, and it's very easy for you to transition to it. But if you know that that's what you want to do, I don't think it's a bad choice to choose to do an undergrad in data science straight away, because, I mean, we know that there are many opportunities in that area. I'm sure if you did a data science degree, there would be components of maths, because there would have to be, and you'd probably start learning those practices a bit sooner. So yeah, I think it would like just depend on your interest. But one thing that reminds me of that I want to say, actually, I know I said that I recommend Python as a language. And I just wanted to just briefly mention another common language that people use for AI and machine learning, particularly in a more kind of academic setting, and that's R. Although I tend to find that Python is used more kind of like in like an industry situation, although it's not black and white. Yeah, so those are my thoughts on that.
Awesome, thank you. It's really helpful for all of us who are trying to decide our degree for next year. So it's really good getting sort of the insight into the industry. We have another question from Jack, and it's about the activation functions once again, and I guess sort of the uses of each one. And he's asked about, so the ReLU is obviously a linear function at a point, and he's asked if, because the input will be directly proportional to the output, how does that sort of, I think what he's asking is, we can see here how the direct proportionality works, but what if it like wasn't directly proportional, and how does that sort of affect the output that you're going to get?
Okay, let's see if I understood. So if we wanted something that wasn't going to be directly proportional, I think we'd choose a different activation function. So for example, we might choose in our first hidden layer, we might choose a tan-h function to constrain our values between 0 and 1, and then choose to use ReLU in this layer. So we don't have to choose the same functions in each layer. I'm not sure if this is entirely answering the question, but we don't have to use the same activation functions. We don't even have to use the same activation functions in each node. So I'm wondering if part of his question is, if ReLU is just linear, don't we just come out with a whole bunch of linear stuff? And I think the way to answer that would be to say that we wouldn't. And I mean, and that's right. In fact, yeah, we would. So we would want to choose like some other activation functions, and only use our ReLU when it's appropriate. I hope that answers the question a little bit, although I'm not sure I fully understood.
Yeah, perfect. I think that is what the question is.
Okay. And feel free to ask again if I didn't answer it, if you have a follow-up. Yeah.
Yes, thank you, Jack. If you have any other questions, we might do the final question. Once again, from Sullivan, in regards to these hidden layers. So he's asked about, so the 4 circles. So I guess if you increase the number of nodes within a hidden layer, how does that affect the output and the accuracy of the model? as such, yeah.
Yeah, so I mean, this is like the previous question, is that in this very simple network, probably if we added, like, let's say 4 more nodes in this layer 1, we might get a more accurate output. And so when we're designing our neural network or choosing our architecture, it's always a trade-off, like between like how much complexity do we add, and where does that stop giving us return? Because computationally, when we add complexity, we need more computer time to process our results. So there'll come a point where, as we add more complexity, and when I say complexity, what I mean is just more layers, more nodes, it stops giving us a more accurate result. And the way that we test that is to look, is to design a few different ones and look at our loss function. So because our loss function is telling us the accuracy of our model, and so model means neural network in this case, if we're using a neural network, because it's comparing the guess or the estimate to our data point, so in this case sales. And so we could try some different architectures and see which one gives us the best loss, and then it's a trade-off.
Yeah, perfect, thank you. I think that might be all we have time for before we move into the next session. Do you agree, Ruth? Is that?
Yeah, I think that's,
yeah. Okay.
Yeah, thank you
well,
so much.
Thank you so much, Ruth, for the amazing talk and taking the time to answer all our questions. As a high school student, it's so interesting to see how the maths that we learn at school can be applied to something as amazing as machine learning and so practical in our everyday world. Unfortunately, Ruth has to go get her workday started in the UK, so we will have to say goodbye to her. And once again, thank you for your time, Ruth. Would I just be able to ask you, Ruth, before you go, would you be able to just transfer the host to me so I'd be able to do the breakout rooms?
Yes, you are now host.
Awesome, thank you so much. And thank you for all your time. Thank you, Emma. And well done for putting all this all together. I've really enjoyed talking to you today. Thank you so much. Bye.
Good night.
Good night. All right, so that concludes our lecture component for this evening. And we'll be now moving on to an interactive breakout room task that will hopefully bring all this content that we've learned about neural networks all together. So, in just a minute, you're going to be assigned to a small breakout room with 4 other students, which you're going to attempt to train data using neural networks. So we're going to do a hands-on experience. So the software we'll be using is TensorFlow Playground. So just let me share my screen. So this is TensorFlow Playground. So the link to this can be found at the top of the screen here. And if everyone could follow this link on their own laptops and get this website open up, and it's going to look like just what I have on my screen here. Awesome. So while you're doing that, I'll talk you through what this program's sort of doing, because right now it looks a bit confusing, but I think we can relate lots of what we see here to what we just learned from Ruth. So within this program, what you're trying to do is you're trying to create a neural network that will train data to create the pattern that you see over here. So this is the data that you're going to input, and you're trying to get it to create this pattern that you can see in the top left-hand corner. So different combinations of neural net structures and the options along the top here affect how accurately it trains the data, which can be seen over in this box on the right. The neural network that you create can then be tested when you click this play button, because this will begin to train the data. As Ruth said, it will choose different weights, and it will train it to select the best weights, which can be seen along these lines here. And it will give you an output of a training loss. That's how much of the data was accurately fitted to the model that you want to fit it to. But don't worry if it doesn't all make sense tonight. This website is a really great resource to keep referring back to as you get a better understanding of machine learning. So in each breakout room, could one of you please share your screen with the TensorFlow playground as you all work together to complete the task. So you'll be in breakout rooms with 4 other students, and you'll be trying to work through one of 2 tasks that will give you time to do. So make sure you get some good discussions going. And yeah, so share your screen and we can work from there. So the first task that you're going to do is to play around on the software, just get familiar with it, and have a discussion about the following points. So as you can see, the nodes are colored in, and these give us a clue of what the data is actually trying to train in each node. So I want you to sort of have a discussion about what the patterns on each one of these nodes means. In particular, how the features, which were these things over here, so the maths functions, affect what's going on in the node. So you can see here, this is a linear function, and so this is just a straight line down the middle, and that makes sense. So have a discussion about the other ones and how they affect the pattern on the nodes. The second point is to have a discussion about what each of the features could mean. So once again, back up here, there's different types. So you have a sine function, dot product, linear. Have a discussion about what each of them means and how they sort of physically translate into what's going on in the neural network. And finally, the last point to discuss is when you hit the play button and you begin training the neural network, try changing the options at the top and see how it affects the training loss value that you get in this data over here. And you can try and smooth out this curve and get the lowest training loss value you can. So please get ready to discuss with us in the chat. Hopefully you can unmute. So just have a discussion amongst us. So I'm going to share the screen with the TensorFlow playground, and hopefully you have it up on your screen as well so that you can be playing around on it as we discuss the following things. So here is the TensorFlow playground. This is my Google. So we can change any of these features here, as you can probably see on your own laptop. So we might just have a discussion about the first point, which was these colored in nodes and what they could mean as we're training each data set. So we might put it on the spiral one, and we're going to see what we think these patterns on each node could mean. So if anyone has any ideas, maybe put it in the chat and we can see. So everyone's pretty quiet, but I guess just the breakout rooms might have helped with that. But so basically, yes. Yeah, so oh, perfect. So I can see the chat now. I just couldn't see it before. So Anna has said that maybe they're positive and negative. So you can see that this linear function here is going in a positive direction, and this one's going in a negative. And that kind of makes sense, right? Because this is a spiral. And so you can sort of, if you're trying to create a spiral, you'll want different nodes that have different gradients because they're going around the spiral. So we have some positive functions and some negative functions that are going in this way here. So that's a really good idea, Anna. And Sullivan has said maybe the colors are two sides of a line. Yeah, so exactly. So we can see here there's two colors. So there's the different data that we're trying to show, and that's what these patterns on here display. Is there any other ideas? 2 almost represents a Y value in the first. Yeah, exactly. So that's a great idea. So exactly, if you're trying to train this spiral and these are linear functions, they're going to look linear. So as Jack says, it's basically y equals mx plus c in this one, where you have a gradient of 1. And so exactly, it's different gradients of different, of different gradients. So now why don't we talk about what these features could mean. So if you wanted to play around on your own and see if you click on some of these, what each of the ones could mean. So these are obviously linear because we can see it's exactly what they are. Does anyone have any ideas what this one, the x1, x2 could be? Yeah, so this one here is the dot product. So it's a maths function that we can apply to it. And you can see here, these are trigonometric. And Josh has asked, do the colors on the nodes mean anything? So basically here, they're just trying to visualize what the data training is occurring. So this is kind of showing that this is what, on this node, it's going to be what this is training. And this node's going to train this. So it's it's the different components, as Ruth had the likes and the shares and the comments. It's the different components of what's going to be trained in each one. I might give you the task to do on your own, the second task, which was to see if you can train this spiral to the best of your ability. So basically, if you go onto the TensorFlow playground on your own computer, and we might have a little bit of a competition. So if you pick the spiral and you design your own neural network, create however many hidden layers you want, change the learning rate, the activation. So these were the 3 plus linear, the functions that Ruth was talking about. So choose all this stuff. I wouldn't change these if I was you. I'd just keep it as the default and press start. You can see the training loss. So we might have a competition of who can create the lowest training loss value, and then maybe they can come on and tell us how they did it and what their solution for the spiral was. Yeah, so give that a go, and then maybe in a few minutes we'll all come back together and you can tell me what the lowest training loss value you got was. All right, so hopefully you're having a think about what it could be. I have 2 sort of hints for you in training this spiral, and they are that try and think about what functions, so the spiral's obviously circular, what functions, features of these would sort of lead you to believe it would help train a circular object. So have a think about that. And also this regularization rate that we haven't really talked about, have a think about maybe how that could affect it and try and play around with that. Does anyone want to be super brave and let me know in the chat what their training loss rate is, and maybe even they could get on and share their solution to it? Or even if you don't have a solution, just talk us through what you were kind of thinking in terms of your solution with this spiral one. Be brave, guys. So maybe you guys are still just playing around with the, so Sullivan says he was just spamming it with stuff. So yeah, that's often a good way to just start out, try and work out what everything means. Jack said that he got 0.057, which is really amazing, especially for the spiral. Jack, is there any chance you wanted to get on and maybe you might be able to share your screen, or even just tell us how you did it? No? Okay, that's all good. That's all good. It is a bit hard. Sometimes it like fluctuates and all that stuff. Does anyone have any idea about what feature they'd probably want to use to train the spiral? All of them? I mean, that could work. Jack said the dot product, and James said the sign ones. Yeah, so when I've sort of played around with it in the past and looked at a few solutions to the spiral problem, they sort of lead me in the direction of the trig functions, because it kind of makes sense. The trig functions will sort of produce somewhat of a circle. So maybe we could start with that, see how well it goes. But as you can see, I'm only getting a half rate of loss. So it's not that good, but I guess there'd be a few more things we'd have to change. Yeah, so this one is, so that could be an option. There's lots of options. So I think the takeaway from this TensorFlow network is to sort of just play around, and as you get to learn more things, Chris has said some complex maths thing, but there's actually, you can get onto the TensorFlow from GitHub, and it's an open source document, and you can actually edit it. So I saw some solutions that used spherical coordinates and that kind of thing. So you can edit it. So what Chris is saying here with a cot and exponential function is that you can get on there and edit the features that you have here to try and make it suit the spiral better. And Anna has said that she found that increasing neurons to an extent made the training loss lower, but then it increased with too many, which is exactly what Ruth said. So that's really great to see it practically, that if we add a bunch of hidden layers, it will just either, it will make it too hard, it will be too expensive to compute it, and it will just use too many resources. So to an extent it makes it lower, and then it just goes up again. So that's a really good point, Anna, and it's great to draw upon what Ruth told us. And yeah, so with TensorFlow, I think that it's a great thing to keep coming back to when you are continuing to learn neural nets. So with the increased number of nodes, that's something we learned today, as well as the activation functions. We could change this, the ReLU, which is the more linear one, all these, so we've learned that today. And it's great to just keep coming back and seeing, as you learn more about AI, and seeing if you can work out, we have classification or regression problem type, and we could learn about that and try and work out what's the best for us as we build our own neural nets. So the only other thing that I have is we have the, this is a solution to the neural net spiral. So if you follow this link, I'll also put it in the chat. And you can follow this link to get an explanation from someone at Google who has done this spiral problem, and they sort of talk you through the best features to use and why they're really great to use. So that's a great resource that's out there if you were interested in the solution to the neural net spiral problem. And I'll put that in the chat as well at the end of the talk, so you can follow that. I think, unfortunately, that's all we had time for tonight. I'm so sorry the breakout rooms didn't work. I'm not sure what's going on there, but hopefully we can sort that out. But hopefully you got to play around on your own with the TensorFlow Playground and you were exposed to this amazing resource. And even if you didn't completely all understand it tonight, if you keep going back as you're learning more about AI, it will start to make sense. So yeah, keep referring back to it. It's a really great resource. But to wrap up the session tonight, I wanted to say a massive thank you to Ruth once again for her time. And of course, Cannon Hill Anglican College, Queensland AI Hub, and Young Women Leaders in AI for supporting this event. And finally, thank you all for coming tonight. And I hope you learned something new about the fundamentals of AI, both from Ruth and TensorFlow. And have a lovely night, everyone.